6 is over here. 1 through 5 is over here. If you're not missing those, then okay. Hopefully people are seeing my screen online and I am talking. That's good. I mentioned the anonymous feedback form. This is where you can give me feedback that's anonymous at any point during the class. That's here inside of modules at the very bottom, right here. Boom. And then folks can fill out the SOTI. How many people are going to complete a SOTI in class instead of doing it? Class. Nice. Okay, at least one. Obviously I want you to pay attention, but if you're going to be distracted by your computer, you're welcome to, use TikTok open, but you could just take on my SOTI. Okay? Tick the boxes. Okay. Questions before we get started? Today is an open house at the observatory. Because the sun sets earlier, that means that the sun sets at 5 or 4:45. And typically I like to open it up to the public about 30 minutes afterwards. That is exactly at class time. So no questions at the end of class. I'm going to book it at 5:15 and go up to the observatory. If people want to ride, I have exactly 4 spots. Okay. And a trunk, but I'm not supposed to do that. Okay. Anything else? Okay. None of those questions are for me. Good. Let's do, have you seen this picture before? Bless you. Have you seen this picture before? What are we looking at? What? Comments. Yeah, where? This thing? Here? Yeah, that's a very good question what that would be, right? It's kind of like there's definitely like outgassing like we saw. So there's definitely ice on the surface. What's that in the middle? Sun, good. A sun, right? And what's this thing here? What? Jupiter, good, good. What's all this stuff? What? Asteroid belt, maybe? Yeah, I like the sound of that. Is this a picture of the current solar system? No, why not? Yeah. Don't put me on the spot. Okay, why not? Yeah. There aren't enough planets. Oh, that's interesting. I only see 2 planets in the picture. Right? That's a perfectly good example. Right? Is this a real photo? Yeah. It's like. Yeah, they're smacking into each other. So that's hopefully not recent. Right? That's big. Right? If anyone lived there, they're gone. Right? After this hits, this will be molten. Whole surface molten, entire thing reshaped. Accurate picture? Did we send the spacecraft to take this? Yeah? No. Anyone think yes? What's the farthest we've gotten outside of our solar system? The answer is we haven't. We have not yet gotten outside of the Oort cloud. The trick question, yeah. Surprise, surprise, yeah. Did it? You tell me. You find that out right now? Gold star. So the heliopause is the location at which the influence of the sun's magnetic field ends. I thought the Oort cloud was outside of that, but you know what? The nice thing about science, you can be wrong. And just say, hey, listen, that guy's right. Right? So this is not a real picture. This is what we call an artist's conception. Yeah.
Voyager 1 has entered interstellar space.
Wow. So how far away is it?
Sorry, I'll say 300 years away from reaching the edge of the Oort cloud.
300 years away from reaching the end of the Oort cloud.
No, 300 years to reach the start of it. start of the work cloud. As it says here, it's currently not even close to reaching it, as it may take around 300 years to reach the inner edge of the work cloud.
Okay, good. All right. So my definition of solar system versus the definition that Voyager wants to use. Okay. So I think about the fact that the Oort cloud is still connected to us gravitation, right? That is the place where all of these comets reside. So I count that. Now, the people at NASA who put out a press release that says, well, we are now in interstellar space because we are outside of the influence of the sun's magnetic field. I don't count that. I think you have to go outside of the Oort cloud. But that's me, you know? That's just definitions, yeah.
164.7 AU.
So 164 times the distance that we orbit the sun. 164 times farther from us. How long will it take for a message to travel to us? Anyone know how to do that math really quickly? Not looking it up. 8 times 150. What's that? 800, 1,200 minutes. That's a couple hours, at least. Okay. So this is a picture of the formation of the solar system, or maybe of a solar system. And we see a lot of elements. So for example, we saw that there are comets, something is smashing into something else. What do we call when stuff smashes into each other? What? Collision, good, but also when we think of it as a heating process, the word we used like 500 years ago starts with an A. What? Accretion. To add stuff is to accrete it, right? So this body right here is in the process of accreting these planetesimals. Okay? They're getting added. Okay, so let's talk about collisions. We showed that the distribution of small asteroids, there are more small ones than big ones, right? And we said, that's very interesting. That sort of matches what craters look like, right? There are more large craters. Sorry, there are more small craters than large craters, right? So we said something along the lines of craters must be caused by asteroids. Do we agree with that statement? Maybe comets too. Now here's the question. Why are asteroids mostly small rubble and not very many big things? Yeah.
They're leftover pieces, right?
What?
They're leftover pieces.
Leftover pieces, yeah, but why are they not all the same size? What happened to them?
Bigger one probably collided with something.
Bigger ones already collided with something, and
Formed into bigger landmass. Bigger.
well, that would seem to suggest that then there would be bigger objects, not smaller objects. There's more smaller objects, right? What? Sun melted what? Oh, right. Yeah. So that's a great question, right? So we're gonna talk definitely about where ices are in the disk today. But I'm just thinking about rocks. I'm just thinking about the rocky asteroids. Why are there not big rocky asteroids and only a lot of small rocky asteroids?
I would guess because the big asteroids split up into smaller asteroids.
What do you mean split up? Like they would stop talking, close to each other?
It's smaller because they hit something.
They ran into each other. And then they did that with a lot of speed and they broke up.
They also double. For a certain lifespan, they don't last very long, so as they travel around the sun, the ice and asteroids also.
Right, yeah, so you might start with a really icy rock, right? But it's long enough, you see that the outgassing here? So then it becomes more rocky and more brittle, right? I make this, you can go home and like take a plate, tell your parents this is for a science experiment, and then start with one plate, right? And get a baseball, and don't have a friend hold it unless you are really good at baseball. and then throw the ball at the plate. Right? What do you end up with? Broken piece of plate, right? Okay, what is the size of the smaller broken pieces of plate relative to the initial plate? Significantly smaller. And how many pieces do you end up with compared to what you started with? Tons more, right? And if you keep throwing baseballs at the pieces of that broken plate, you end up with more and more small pieces. So this is called collisional grinding, okay? So this is how we know that asteroids don't just like to link up and like become friends and become bigger, because otherwise we would find larger, big asteroids. Instead, what happens is they tend to smash each other up, right? Grinding each other into dust. Okay, what happens in the solar system? So right after the solar system formed, there's all this trash, right? Planetary debris. And yeah, not so fun if you lived on that surface, because you get these big old bangs, right? And we can tell that there was a period by looking at the distribution of impact craters on the moon. We can see there was a bunch of impact craters, and there was one period where there was a lot of impacts, and then it kind of went back to normal. And we call that period the period of heavy bombardment. And we might just get to what that is today. Depends how quickly we get through it. Where did the water that's in here that I'm drinking come from? Don't say the tap. Asteroids. Yeah. Icy asteroids and comets, right? And in order to do that, they don't drop it off like it's the Sparklets man, right? They need to smash into the surface after the surface is no longer molten. So you have to wait for the planet to cool enough that it has a nice hard surface, and then you got to smack it with little asteroids that give it enough water to make oceans. Okay? And water certainly doesn't come from volcanoes, otherwise Venus would be great to live on, right? Okay. Here's us, cross section. So, wow, just being how good Europe is here. They really did a good job of forgetting an entire African continent. Okay, maybe this is like before. This is like the past. Yeah, Africa's like on the other side. You can't see it yet. It's not there yet. Okay, so here's the core, big core, nice mantle, Earth. Here's the moon, small core, big mantle. Huh. Here's Mercury, big mantle, no, big core, small mantle. Has that bothered anyone the whole semester? Raise your hand if it's bothered you. Yeah, okay, cool. Real geologist in the house. So we can explain this with a couple different collisions, okay? So we're gonna start with talking about the Earth-Moon system and how us and our nearest neighbor have very similar compositions, but for some reason they have very little core, okay? How do we know they have very similar composition? How do we know that the moon rocks are basically Earth rocks? Yeah.
We went there and we got them.
We went there and we just got bags and bags of souvenirs. I mean, the gift store was very cheap, so we grabbed everything we could and we got back on and we brought them home. Now it turns out, coolest thing about bringing a sample home, you bring a little piece of the moon home, that as long as you keep it in really good conditions, then you can bring it into a facility that you develop 30 years later, and it can still look at that same rock and find out new things about it, right? That's the coolest thing about returning samples. So people are like, why did we go to the moon? Well, it's mostly for dorky geologists, but you know, it's pretty cool, okay? One of the main things they found, this stuff here, basically exactly like that stuff, like exact. Only thing that's missing is some stuff that likes to evaporate very easily. Like there's not a lot of water in the crust of the moon. And there's lots of water in the crust of the moon. And there's some other isotopes that I'm not going to tell you about. And this leads some folks, particularly one scientist at SWERI. She's thinking about all of this information in the 90s. Remember that your parents did not know how the moon formed. They learned about it before you were born and potentially when you were a youth. Okay. So Robin Knupp is a scientist at SWERI, and she's like, I think the moon hit us, drunk driver wise. Let me show you. Okay. This is the giant impact hypothesis, because people were arguing for a long time whether or not the moon kind of like formed nearby and we like captured it and we're like, oh, best friends, you know, let's hang out together, or if it was like smash. Okay. And essentially in the early 90s, there's just too much evidence that one of them smashed into the other. Okay. So what probably happened, and I'm going to show you a simulation of this, is there was an object, we call that object Theia. It's the precursor object. It smashes in to the Earth, and then it creates a disk, and that disk really rapidly became the moon. Nothing was forcing it apart anymore. Okay. This explains why the compositions are so similar, because that's what the moon is made of. It's made of the Earth splashed off, right? And it explains why we don't find a lot of water, because that water, when it gets very hot, would just evaporate. It would go into the disk, and the disk would just evaporate it away. And then when it formed into the moon, you wouldn't have much of it left. Okay? Yeah.
Does that mean Earth had rings at one point?
Yeah, this was Earth's ring. So anytime you go and you look at the moon, you're looking at the result of Earth's ring. Yeah, that's fun, right? Like a cute way to think about the moon. By the way, we'll look at the moon tonight. Okay. So here's Theia. And likely we have, good reason to think that most planets, they start rotating kind of normally. So as they go around the sun, they coalesce, they become a ball, and that ball spins in the same direction as the disk. So the disk is going around like this, and the object's going around. And the orientation of the planet is probably straight up and down. We see that for Jupiter. Jupiter is like straight up and down. Nothing is knocking it on its side. Nothing is turning it, right? So Jupiter and Saturn almost straight up and down. Okay. But then Theia's like, nope, I really want to get close to you, and smashes into the Earth. And it does it at an angle. See this? So up to the side at an angle to the axis of rotation. And it does it at a glancing angle. So instead of hitting it, you mind if I brought this? Instead of hitting it straight on, it hits it kind of to the side, right? And hitting it kind of the side is really important, because that's the only way not to have this object either sink directly into us. If you hit us straight on, you just go right in. You hit it from the side, you can at least throw this material off, and the material that you throw will be the mantle, and not a mixture of the mantle and the core, right? So that's what these simulations were able to show in the early 90s, was exactly what angle was allowed. And it's a very small window of angles. Any other type of impact does not reproduce the moon. Okay. And that's the debris. That's not a very pretty looking disk, but I'm sure it looked gorgeous. One, because it was really close, and two, because it was hot, like physically hot. So it was like this bright, beautiful disk. Of course, you were dead on the surface, but if you were like an alien somehow with like, I don't know, floating above the surface, I don't know, whatever. Okay, and then you get the moon. Cool, right? Okay. Here's the simulation by Robin Knupp in 1996. You will see computers got better. Okay. So this is a type of simulation where they model individual particles here. So each one of these individual pieces is being simulated for gravity, for composition. They're looking at how hot it got. They're looking at what it's made of, right? And this is the debris disk. I don't think there's a time in the bottom. That would look really cool, right? Yeah, and this is the glancing impact. Okay, and this explains why it orbits in the same direction as Earth. This explains why it has a lower density than the Earth. And this explains why there's very little water and oxygen and whatnot, right? Okay, so people are still working on this, and computers got better. So let's watch a modern version of this simulation by the same folks. And let's use more particles. So sometimes if you're working on a problem, you just got to wait for computers to get better, right? You do like a shitty job first, you're famous for a long time, and then your grad student works on that. Okay? What? Oh yeah. Algorithms, am I right? Okay. So does this explain anything else we've seen in the solar system? This new idea of smashing shit into shit. Yeah. What's wrong with the Uranus? It's upside down? Like this, right? It's tilted completely on its side. That's weird. Yeah.
Mercury's at the top, right?
I don't know if it's Mercury. Venus is upside down. And its day is as long as its year, right? Or they're about the same. So that's weird. Okay, any other weird thing? Yeah.
Well, how do we know it's upside down? Like, how do we know that that's upside down and not upside down?
So you're saying like, how do we know that like we're not rotating in the wrong direction? So we're rotating in the same direction as the sun. And we're rotating in the same direction as all of the other planets except for. So that's why we decided that Venus is going. Now, why did we decide that north is in the direction that north is? What? Colonialism. Right? Because where are the majority of the people? Where's the majority of the where's the majority of the continents with respect to the North and the South Pole? The North. And where are most of the people in, say, the 1600s? In the North, right? Okay. Is that it? Just Venus and Uranus? And Pluto? What's wrong with Pluto? Oh, Pluto also tilted on its side. That's true. Anything else? I don't know if I showed that. Could be true. Could be true. There's a lot of moons, right? So especially with Jupiter, Jupiter has both regular and irregular moons. It's got a couple that are like kind of how we would expect moons, and then some that look like they're like a little orc cloud around Jupiter. They're like go like this, and the rest of the moons are like that. Okay. So yes, that's Uranus tilted on its side. So people say, well, maybe you smacked into it with something. There may be another explanation for this. We'll talk about that in a few seconds. This one, you guys want a tangent? Okay, all right. All right, let's think about how we discuss things, like how do we know stuff scientifically, right? So I gave you this claim about the moon being made of Earth stuff, Earth mantle. So there's a very famous planetary scientist who got up at a conference once and said, I think I know how Venus got its peculiar rotation, but we can't find out if that's true. Okay. So we said that Venus's surface is at most anywhere on the surface 600 million years old. That the entire thing melts about every 600 million years. Melts completely. Because it doesn't have plates. It doesn't have enough, it doesn't have an ability to let that heat out. So the heat builds up until the entire crust melts and it overturns. Okay? This is just something that happens on Venus. And he said, okay, maybe what happened to Venus is something very similar to what happened to the Earth. Maybe it formed a moon. Now, the moon was actually closer when it formed. And throughout the 4 billion years, the moon has been moving away from us. We know that because when we went to the moon to pick up those rocks, we left it a present. You know we left the moon? What? A flag, no. Yeah, we did leave those too, but that's just littering. Yeah. That's also littering. We left it something nice. We left it a mirror. So we left a very special kind of mirror that looks like the inside of a box, like this, where it's mirrored here, here, and here. So that if I shine a laser, the laser will bounce back in exactly the same direction that it came in. And we have been shining a laser into that box since we landed. And what we do is we send a little pulse and we see, hey, moon, how far away are you? And we've been able to tell that the moon is very slowly receding, moving away from us. Yeah. So many billions of years ago, it was probably quite close. Not close like, oh, you can touch it, but close, right? And at some point, many billions of years from now, it'll be much smaller in the sky, so much so that it'll eventually decide that it doesn't want to be with us anymore, and it's going to go live with the sun. Yeah. Yeah, but we'll be dead. Don't worry about it. Okay. So what ends up happening is that as the Earth rotates, there are tides, and those tides are attracted to the moon, and that acts to slow the Earth down and to slow the moon down. And as they slow down, they have to move apart. Okay? I'm just telling you that. But a weird thing would happen if the Earth was rotating this way, and the moon was not rotating in the same direction. If it was rotating in the opposite direction, you would actually get closer. So David Stevenson said, let me propose an untestable hypothesis. Let me propose that the Venus got hit twice. First creating a normal moon, rotating in the same direction, and then creating, like getting hit in the opposite direction, changing its rotation 180 degrees, creating whatever moon, he doesn't care. But now that original moon that was going in the original direction starts moving towards Venus. And along the way, it picks up the smaller moon, smashes into the surface, and both of them disappear forever. With the only evidence being that now Venus rotates in the wrong direction. Is this science? No, it's not testable. Right? There is no way to create a test for it. Because the surface is gone, right? Now, if you get a little clever, you might be able to say, well, during both of those two original impacts, maybe stuff flew off, and maybe some of that stuff landed on the moon, and I can go pick it up, because it hasn't been messed by anything on the moon. It just sat there for probably 4 billion years. But that won't tell me about the rotation. That won't tell me that there's 2 massive impacts that resurfaced the Venus, right? So this is very close to untestable. This is like on the verge of what happened before the Big Bang. Yeah.
Are there any moons that are currently approaching their planets?
No, because they get turned into rings, right? So this is exactly what happened to Saturn. Saturn probably had some moon that was in fact getting closer and it got shredded, right? And of course, Venus probably had a really beautiful ring system before, well, the objects. Okay. Isn't that fun? It's like a fun storyteller. Yeah.
So like, are moons between us?
But not, don't, it's not like this week.
I know, but
Yeah, okay.
like eventually, does that mean it's gonna become its kind of like own fourth planet eventually?
Yeah. It depends. I mean, so when people do simulations about the long-term stability of the solar system, I think what ends up happening first is that the sun becomes a red giant, and that really fucks everything up first. Just because as a red giant, it begins to lose mass, and it expands, and it gets to the size where it like swallows the inner solar system. Yeah. So moon is like it's already. Okay, but that's fun, right? And we can understand that story. Did you tell it to a friend? Okay, I'll put that on the exam. Okay, probably how you get Pluto and Charon. They're probably friends, or like a series of friends. And there's like 5 other moons there. They're kind of all going around in the same direction. So that was probably a debris system as well that just Pluto hasn't cleaned up, hasn't cleaned up his room. We started off with the picture of Mercury and Mercury's large core, and then I really didn't talk about it again. But that's an explanation for maybe how you form Mercury. So Mercury, how do I say this well? When we talk about theories of planetary formation, you should have more stuff to build planets with closer to the sun than you do at Mars. And that would theoretically explain why, for example, Venus and the Earth are larger than Mars. But Mercury is smaller than Venus and the Earth. And an easy solution to that problem of it being smaller, and to the fact that the core is the most of the planet, is that a lot of Mercury got smashed off in a collision, similar to the one that we had, but more of a glancing blow, ripping off the mantle, and then that mantle just falling into the sun. Is that fun? Is that testable? That one surprisingly less untestable. Let me just say that differently. Because we know the composition of these objects, you have to be able to reproduce the core and the mantle, right? So this is an unusual problem already. Venus's unusual problem doesn't have to do with its interior, right? So you can simulate early solar systems. You can put more material or less material by Mercury and see how can you build something that's mostly core, right? And one of the only ways to build something that's mostly core is to have a normal sized planet and to shave off the mantle. Because how do you get a core? You have to have a big object, got to melt on the inside, and the heavy stuff has to sink. Right? So it couldn't have formed this size. Because it wouldn't be big enough to hold all that heavy stuff and melt it, right? Some planetary, they're called cosmochemists, and they're sick. They like know everything about rocks, but then they know everything about like how asteroids move and like the history of the solar system, and they figure all this stuff out. Okay. All right, so let's think about I've said a lot of words. Let's think about creating a story or theory for the formation of the solar system. Okay. We need to explain, we've seen over the course of 11 weeks or so, we've seen a lot of evidence that we need to explain how it happened. So, what can we tell about the formation of the solar system? We have 8 planets. Don't come at me. They all are in the same disk. That's kind of weird. Kind of all orbit like in the same plane. Like the Earth isn't like up here going up and down. Neither is Jupiter, right? Some moon systems do the same thing, right? Jupiter and Saturn have moons, like we just talked about, what we call the regular moons, that seem to form disks around them. We saw that there's 2 types of planets. There's the rocky ones, and the ones that are gas all the way down. Needs to be able to explain that. We need to explain that there's 2 types of small bodies. What are the 2 types of small bodies? Asteroids and dwarf planets. Yeah. Another way you might say that is like just by composition. Ice and rock, right? Yeah, that'd be the easiest way to explain it, right? So ice and rock, gassy and rock. Okay. Oh, maybe there's a theme there. We'll find out. And then there's some exceptions. Right? Every theory's got to have an exception. Okay. Any questions? All right. What's that? Deadpool? Sauron? Okay. This is called a protoplanetary disk. So when we talk about the formation of the solar system, we're going to kind of go outside of our solar system to begin to understand how we could have formed and how we can build lines of evidence to understand a time period before we were there. Now, this is not a real photo. This is a artist conception. But what you'll notice here is there's a few things I want to point out. There is a proto-sun or a sun, whether that's like just forming or it has fully formed. There's something that looks like a disk, and then there are little baby planets. And where the material is falling onto them, it's heating up the disk. Okay. So here's our challenge. We have to be able to explain all of these. And we're going to go one at a time, trying to explain every single one of them. Okay. In order to do that, we have to understand stuff about stars. Okay. So we're going to use our solar system. We have our constraints. Okay. I'm going to teach you today and tomorrow a little bit about like chemistry of how stars form and where we come from, like this stuff, right? Nature. And then towards the end of like 2 or 3 weeks from now, we'll see things that prove this wrong. Okay? Okay. All right. How does the sun form? Yeah. Mm-hmm. Yeah. Seems anticlimactic, right? Yeah. Stars are just gas. What kind of gas, by the way? Hydrogen and helium, predominantly, right? 70-30 almost. And like what makes us makes up like 1% maybe. Okay. So let's understand that. If I look at this room, I would guess no one's older than me. I would also guess everyone's over 18. Okay, so there's sort of like a median distribution of ages here, right? If I include myself, there's like an outlier, right? But I can kind of see how maybe different points in a person's life, they might undergo changes. Whether that's changes to their facial structure, changes to like, wrinkles, like stuff like that. And if I took 100 people of different ages, I could kind of sort them, right? And say, oh, the smallest ones over here, those are the youngest. And I might accidentally misclassify some elderly people with them, but then I'm like, oh, wrinkles, right? So wrinkles are, so people will get, start small, get big, get small, but with wrinkles, right? And that would be a way of looking out at a population of very many different things. And I don't have to wait 100 years to do it, right? So we don't need to wait 4.5 billion years to figure out how the solar system works. Because if we look out and we see thousands of solar systems in different processes of formation, we can fit them on a timeline, right? And say, oh, this must have come before this, and this must have come before that, right? So we can use different stars of different ages to test our planet's theories of star formation. Okay. Nebula, if you've been to the observatory, you know what that means. Just means smudgy stuff that you see, right? And in Latin, it means mist. Nebula means like a cloud. Nebular means cloud-like. They are not clouds. I say dust cloud. It's a different version of cloud. Don't think like water. Think like dust in space. Okay. All right. Let's look at pictures. No sleep. Or if you're already sleeping, wake up. Okay. This is the Orion Nebula, or the Trapezium cluster. And thankfully, there's a fall, if you just wait till like 10 p.m., you can see Orion. So this is in the middle. So like if you look at Orion's belt, you guys know Orion constellation? He's like this, the bow and arrow. It's like here, like in his belly. So if you just point your telescope at like right above the belt, the little empty spot, you will see this. On the left-hand side, this is invisible. In fact, it doesn't really look like there's a lot of stars there. It looks like a lot of dust, right? And that dust has a lot of really cool structure, maybe like 1 or 2 stars. But on the right-hand side, this is the infrared, which lets us look through dust and see heat signatures. And from that, we can see tons of stars that are forming there, including some really, really bright ones. And in fact, these ones, these new bright ones, they are so hot that they are blowing away the dust. So after they formed, they were like, no, we don't want any more material. Thank you, we're full. And they're spitting out heat and particles and pushing away the dust so that no other stars form. Okay. Here is another example. Okay. On the left-hand side, Hubble is in the visible. This is what you would see with your eyes. And on the right-hand side, JWST is again in the infrared. And you can see a lot of the same stars, right? These two here are these two. They're very bright in the infrared because they're very hot. This is all dust that's forming these objects. Okay. Let's zoom in on this picture on the right. This is the coolest part, by the way. If you want to go home and you're really bored, you can just type in JWST picture repository, and you can open up one of these, and they're like 21,000 by 21,000 pixels. You just like zoom in as much as you want. Super rad. Okay, So that was a star called Uranus A. This is, sorry, the Orion Nebula. I forgot to mention that. Over here, this little dot, this little smudgy thing, if you zoom in, this is a young star. And this is it forming inside of its little bubble cocoon. Right? And this one over here, that circle size, the little circle you see here, that's the orbit of Neptune to scale. So if I look very closely, there's the little cocoon that it's forming in. And that little white thing, that's the disk forming around a brand new star. Right? Over here, we see all these filaments, these filamentary structures. These are places like rippling gas clouds. But unlike normal gas clouds, when these ripples get too close, they start to gravitationally attract and they collapse and they form these little cocoons from which stars form. Right? So you might end up with, and I'm not saying it will happen here, but you might end up with, say, along a filament, a number of stars being formed, right? As these little places collect mass, and then those masses turn into stars. Familiar with this picture? Anyone know what it's called? Very good. Okay. What is it? What? Stuff. That is exactly correct, and the scientific term. So this is stuff. It's dusty stuff. And this is a nebula, which just means like cloudy stuff. And this is in the visible. So this is with the Hubble image. These are really beautiful. This is what it would look like with your eyeball. But this is what it would look like in the infrared on the right-hand side. So they're called the pillars of creation. You can see here, here, these are like pillars. But all of this, right, is like gas and dust. Like even just look in this section here, you can barely see any stars. And if you look over here, there actually are tons of stars in the background. You just can't see them because it's so dusty, right? And similarly, up here, there's like where the stars are forming. And you can see in here, these little stars are forming right at the edge, right? This one is that one. Okay. This is cool. Anyone know what this one is? So you would make that. That's the dust. What do we expect to be in there? What? A star. Yeah, at least one, right? So that's in the infrared. That's in the visible. That's in the infrared. That's in the visible. All right, Red. Gonna see through the dust. And sure enough, there's your offenders, right? So inside of these like filamentary structures where gas is collapsing, you see these bright hot stars, right? These ones right here just formed right on the edge. This guy out here, you'll notice, he already blew away his filamentary structure, right? He's like grown up. He's like, I don't want to be part of your family, right? Right there. You can't see anything over here, right? All that gas and dust is not leading to anyone. Oops, go back. Sorry. Try to see if I can see anything else here. Same dudes. Same dudes. I don't quite know what these structures are. I'm not actually an astronomer. I'm a planetary scientist, so assuming. Okay. This is one of my favorite. You see it yet? Yeah. Okay. This again is the Keyhole Nebula. And this is in the visible. If we look in the infrared, this is what it looks like. And you can see that it's just punched a hole into its nursery. Real or fake? Real. Isn't that stupid? Like space is so cool. And like we look at places like this, like nebula, like I can't draw, but I couldn't draw like that. Like not even if you gave me superpowers. Because I want you to remember, you can go online, and I really encourage you to get this photo expanded. There is structure all the way down, right? All of this filamentary structure, this is where new stars are going to form, all in these enhancements, right? And then once a new big star does form, it just blows, like it's like blowing away the cobweb, right? That's gonna push away all that gas and dust. Okay, another great one. Right? Just like punching a hole in the gas cloud that it formed in. And if you saw, came to the observatory before and you saw a little like planetary nebula, it was like different colors, like rainbow, the dot in the middle, it looks like that, different reason. Okay. This is one of the problems with nebula. It's a nebulous term that doesn't explain what it means. Okay, so that's all the fun pictures I have. I'm sorry. Oh. So where did the elements in the solar system come from? What? Hobbits? Comets. No, sorry. Let's go even bigger. Go even bigger. Where did like all of these come from? Yeah. Stars, okay, that exploded. Okay, I like those words. What made the stars? What? Gases? Where'd the gases come from? Ah, there we go. Okay, so now we need to have a start because we as humans feel that time progresses, right? So we have to go back because we can ask the question when? Before. Okay, so there's the periodic table of elements for you and I. Right? What was the first element? Hydrogen. Good. Simplest element. And then? Helium. Good. And then? Was it? Do you think they just were made in order, like 1, 2, 3? This isn't like a Build-A-Bear workshop, you know? Okay. So we're not going to be able to go into Big Bang cosmology in detail. I mean, I could do a separate lecture on that if you want a bonus lecture on it. We can do nucleosynthesis if you want to know how you build all of these. But this is the astronomer's periodic table. It's super easy. You know, being an astronomer, the joke. Not just kidding. So immediately after the Big Bang, this is all you have in the entire universe. It's about 75, 25. Okay. Yeah, I'm not going to explain why. Okay, so you create these two in the Big Bang, and then you make more in stars. Hydrogen fuses into helium. That's the reason why the sun has not burned out. If you're curious how they figured that out, in the late 1800s, 1870 or something, they were like, yeah, so we've been measuring a lot of stuff, and if the sun was made of TNT, it would have burnt out. All of it would have exploded. And they said, we can think of no material that would burn long enough for the sun to not have burned out in 15 million years. And yet they already knew in the 1890s that the Earth was 4 billion years old. So they're like, something's wrong. And you may have heard of this guy named Einstein. Heard about this? What's he famous for? Haircut. Haircut? That's true. That is true. Theory of relativity. Okay. Maybe even less. E equals mc squared. What does that mean? What? No. That's what the letters are. What does it mean? Then we know what the E means. Energy. What does the M mean? Mass. What does the equals mean? You're doing like the opposite of a word problem. Is. Energy is mass. Mass is energy. So the reason that E equals mc squared is so famous is because it is the recognition that matter itself is energy. And that is how you create tremendous amounts of nuclear power, both in terms of fusion, like what happens inside of stars, and fission, like what happens inside of nuclear reactors or bombs, right? And basically all you're doing there is you're starting with something. Yeah, awesome. Okay. Chalk. Okay. Imagine I had 4 pieces of chalk, which I did. Okay, but you may not be able to see them. Okay. I have 4 pieces of chalk. And you weighed them, and you're like, oh, that's 4 grams. And then I went like this really hard, and I pulled out 1 piece of chalk. That was almost the same size, but just like 3.9 grams. Then in that process, I would create energy. This is taking 4 hydrogen atoms and turning them into 1 helium atom. And in that process, you get energy. That's fusion. That's why the sun is shining. No fun? Okay, so that's the simplest way to show it. We can go into a lot of detail if you want to, but it might hurt. Everything else, carbon, nitrogen, oxygen. So we are made of schnops, CHNOPS, carbon, hydrogen, CH, and nitrogen, oxygen, phosphorus, and sulfur. That is necessary in order for anything to survive. And I guess everything except for the H in that is made in the interiors of massive stars that have since exploded and belched their remains back into the solar system to make that dust that we were talking about earlier. So right after the Big Bang, maybe you form a really beautiful star, and maybe you even get a nice pretty disk around it, but you get no planets because you don't have anything to make planets. You can't make planets with just hydrogen and helium. You're saying, well, Mateo, Jupiter is hydrogen and helium. Yeah, but it probably started off as a core, and it probably used the fact that there are ices. All right, we'll argue about that. Okay. So after 4.5 billion, or sorry, 13.7 billion years after the Big Bang, this is the current state of affairs. It's mostly hydrogen, a little bit of helium, and then this is what we're made of. Right? Pretty cool. The amount of non-hydrogen helium is 2% of the total amount of all stuff. So in 13.7 billion years, you have converted this. Remember, this was 75 and this was 25. So 5 of this percent went to 3 of this percent and 2 of this percent. Right? So if I were to ask you the question, what happens in another 13.7 billion years? More tiny stuff. Okay, interesting. Interesting. Okay. What would the astronomer's periodic table look like if the universe aged 13 billion more years? Would A look exactly the same? B, H would be a little smaller, but not much. Other elements a little bigger. C, H and E would be pretty much all gone, all converted to heavier elements. D, all the elements would be the same size, that is to say, the same amount of everything. That's not the same as what it started with, like equal amounts, right? D is equal. 2. Okay, you haven't voted. 3, 2, 1. All right. We got a majority for B. Does that make sense? Let's look. It says the H should be a little smaller, but not by much. All the other elements a little bigger. Yeah. That's pretty good. That's exactly the same, right? So you'd still mostly have hydrogen, probably down to something like 65%. Maybe less because it's getting more efficient, like bigger objects. So maybe if you want to be like generous, like 60. Maybe something like 35, 40% helium, depending on how you want to do it. And then the rest is just a little bit of us stuff. Okay. Questions about this? Okay, so that's giving us where we got everything. Now we have to understand some physics. Oh no. Okay. Let's do the first part. We're going to learn about conservation laws. You ever seen this demonstration before? What happens? What goes back and forth?
Little ball and then-
Yeah, so the ball comes. Sorry, go ahead.
It's going back and forth, but only the ones at the end.
Yeah, so this one comes in, hits this ball, and then this ball like flies off, right? Yeah. And then this one comes back and it makes the other one fly off. Right? Okay. So this is an example of a conservation law. And we're going to describe a couple conservation laws today. How do you get an ice skater to spin fast? Can you do that again? You pull in. Okay. Where does energy come from? Very good, very good. In fact, that is the only correct answer, but not the one I want here. What's another example of a place that energy comes from? So all energy, of course, comes from the sun, right? At some point or another. So the right answer is certainly mass, but not the one that I wanted here. Yeah. The outlets, yeah, that's right. So energy comes from outlets, good. And where does the energy in the outlets come from? Power grid, and where does the energy from the power grid come from? What? No, solar panels, right? And then the sun. Okay, that's one way to go back. There's many types of energy. Like if we're in green California. But what about red West Virginia? Do you think they have solar panels? No. What? Coal. Good old coal, right? So how do you get the energy there? You burn it in a coal furnace. Good. Okay, and that turns a steam turbine, and that steam turbine makes energy. Okay? Where'd the coal get the energy? It's what? It's carbon. How did the carbon get energy? The sun. That's correct. What is coal? Coal's not the sun. You're close. You're close. Creatures or plants? Because creatures are not plants. I would not say that a tree is a creature. I mean, hopefully. Right? Petrified forest makes coal. Right? Under pressure. Ah. Okay. So can I lose energy? Yeah, my phone definitely loses energy through the course of the day. So I gotta plug it in like 17 times a day. Okay. Can I make it? Yeah. Obviously, you just turn on the light. Right? You just flip the switch and energy's made. Duh. Okay, so let's talk about the first one. Here's how we conserve angular momentum. Now, when I have a ball on a string, which I don't have, I probably shouldn't do that anyway. Should I do it? No. Oh. Okay. Yeah, right? Well, you won't see me that much, right? Okay, so this is going around in a circle, right?
Yeah.
Okay, what happens if I put my hand up? Stops, but it's spun faster first, right? And it slows down as it goes out. Now, this is not an exactly good example because it needs to keep spinning to show that it would spin faster, closer, right? But what's happening here is that angular momentum is being conserved. What I mean by that is there is a property called momentum, which we saw earlier with those balls. One ball hits the other ball and it moves them, and it can be transferred, right? So you are familiar with the idea of momentum if you've ever played flag football and maybe someone gets a little too carried away and it becomes tackle football, right? That is momentum. So if you are a really big person and you get hit by a small person, what happens? They like bounce off you. They don't transfer very much momentum. But if the roles are reversed and you're a small person and you get laid out, right? Then they transfer all their momentum into you. They stop and you go, wow, right? Okay, that is a version of linear momentum. I'm moving in a line and I'm transferring something that is the product of the mass, size of the object, and how fast they're going. So for example, a very small object like this doesn't seem very dangerous, right? But if this is heading at you at 400 miles an hour, slightly more dangerous, right? Yes, well, I'm not going to do that at school. So the idea of momentum is that it is the product of these two quantities, mass and velocity. And for the purposes of what we care about here, we want to know this different type of momentum. It has to do with rotational motion. And we can define that as angular momentum, which means that I choose some point here. Where did my thing go? Oh. I choose a point that I'm orbiting around or I'm moving around in a circle. And this is going to have this property of going around in a circle, going around in a circle. And if I want to change a property, like the radius, how far it's moving, or if I want to change how quickly it's going, the other ones will have to change as well. Okay. Okay. If this thing is conserved, right? I claim that this angular momentum thing, it's conserved. What happens if R goes down and we assume that the object doesn't change in mass? I know it looks like scary math, but it's not scary math. Okay, that it? Final votes in 5, 4, 3, 2, 1. Okay. Looks like the class is about half split. So why don't we try to find someone who has a different answer than you? If you have the same answer, let's move around a little, make a new friend. Make a new friend, turn around.
But it's not. But it's saying you want to say movement, so that's where my head was at. Because the only thing you can tell me, it'd be like that. See, that's where my head was at. How do I say it?
Oh.
I guess like the plan, you can over how it like.
Oh, this was, you just gave it to me. I didn't. I was like, what was it?
You gave it to me.
Last time. Okay, okay.
Oh, yeah. Yeah, that's what my nose like too.
Okay, click in when you're ready. Okay, early answers are in the lead. Click in if you got it. Five, 4, 3, 2, 1. You did a really good job of convincing your neighbor. Almost everyone has it here. One person has gone to E. That is not correct. That is also not an option. Okay, so since you did a really good job of explaining it, does anyone want to explain it? Maybe someone who hasn't talked today? One of the back row, perhaps? Also some nice discussions up there. Someone in the second to back row? Okay, any row? Someone who hasn't talked today? I know, but you can't just have the same voices. You gotta have a diversity of thought. Yeah.
Demonstrated earlier in class that as the radius gets smaller, we're spinning the beams that the object spins faster.
It's true. I did do that. I guess I shouldn't have done that. Fuck. All right. All right. Never mind. Okay. So that's the reason why ballerina goes then. Okay. It would be C. Faster, right? Yeah. R gets smaller. You go fast.
Like a tetherball.
Sure. Yeah. Yeah.
These systems, one thing, as a kid at the park, that just kind of went around and around. And I noticed that as I, have onto my hands, but lean myself out.
Yeah.
I would go slower. and
Yes.
Leaning further into the.
That's exactly correct. Yeah. They make, I don't know how children do this. They make these little spinny things, right? I did it as an adult, like in grad school. And then you do that, right? You fall off. Yeah, I don't know how those are kid friendly. So this is how, oh, this is not a ballerina, this is ice skater. Look, see? Tiny details. Okay, so this is conservation of angular momentum. We need this concept. We're not done. We have 3 minutes. Okay. And now we have conservation of energy. So I'm going to claim that all energy is always conserved. No one got upset by that? Okay. So I will claim that when you go up the hill, you're using stored energy in your body in the form of calories. You get up to the top of the hill. You now have potential energy. You've converted the body energy, that potential energy, that rolling energy, into energy that can be re-released, like a battery. And then you roll down. Best part of any bike ride is the downhill. And you go fast. Whee! Right? So this is conversion between different types of energy, but at no point was energy generated. So at this point, energy was taken from the body and put into the rotation of the tires and made the bike go up. And then on the way down, you got it back just by going fast.
Just thought about the effort, right? Effort going into pedaling and then.
Yeah.
But then for energy, yeah, would you be pedaling because downhill?
No, you wouldn't pedal at all, right?
Yeah.
So where's the energy go though?
It's stored, you're not using it until you like,
But you're going fast now,
yeah. But once like if you slow down a little bit, you start pedaling again, right?
right? So interestingly enough, if you just keep going, right? Then you could just keep going, right? You have speed. Why do you slow down? Friction. And friction is what? It's actually a heating process. So if you take your hands, and you can do this, you potentially have done this before, you can remove a layer of skin and you can make your hands hot. That is friction. That is turning motion, kinetic motion, into heat. Right? That energy is still there. You just don't have access to it anymore. Okay. We'll do the rest of energy and then we'll talk about solar systems. If you want to come to the observatory, wait like 5 minutes for me to get to the gate. Okay. Homework 7? No, not yet. That one